Okay, so I promised Ben I would walk around a little bit so we can use this special camera on a tripod. So what do people think about the logic programming stuff so far? Is that interesting? Has anyone seen? I mean, if you've used Prolog a lot, you've seen the append example probably, but I'm going to show you something you haven't seen before, I'm pretty sure.
Are you also going to talk about why negate is hard? Is it possible, or is it like...
Yeah, how to talk about negation. What to say about negation. So it's my personal pet theory that essentially all research and logic programming is trying to deal with negation because it's that hard of a problem. The problem ultimately is that this is a constructive model of computation, right? So we're basically constructing a proof that an answer exists, right? The problem is if there is no answer, then how do you construct a proof that there is no answer? In particular, if you have negation, then what you really want is a proof that there is no answer, and then use that proof to then go on and prove something else. And so I think it's the constructive nature of this that makes it very tricky. And it's sort of the sorts of things that you see in intuitionistic logic, which has, or constructive logic, right, where basically, if you want to talk about some object, you have to be able to prove it exists, or if you want to talk about a property, you have to, construct a witness saying, hey, here's an object that satisfies this property. You can't just talk about it abstractly. So I think that's ultimately the biggest problem.
So it's going to take like a whole different approach then, basically.
So you can do a couple different things. So there are ways you can cheat in a way. So you can use something called the closed world assumption that comes up a lot. So basically, the closed world assumption, the way to think about that is if you have a train schedule, okay, so you have the track schedule. If you look at the track schedule and it says the train is leaving at 8 o'clock and the train is leaving at 8:15, is there a train that leaves at 8:13? No, because otherwise it'd be on the train schedule, right? So that's the closed world assumption saying, hey, you can think of it as we're going to list all the possibilities in a database, and then you search, you do a query, and if it's not in the database, then you know it's not there. Okay, so you can use the closed world assumption, you can use that model of the world along with sort of a way of pruning the search tree, or a way of, so not really pruning the search tree, a way of committing to going down the search, going down part of the tree, the search in a way, or committing to one Condi clause. If you have a Condi clause, say, okay, we're going to commit to this clause, but not the others, instead of trying to try all of them. So you can use this committed choice. You can use a couple of the operators like that, cut and so forth, to say, okay, we're going to try something, and if that doesn't succeed, if there is no answer, then we're going to say, we'll go to the next Condi clause, okay, and then do that instead. But otherwise, we won't try the other Condi clause. And miniKanren has an operator like that, has two of them, called Conde and Condu, that are these committed choice operators. So that will allow you to do a form of negation based on this closed world assumption. But maybe you're dealing with the web, for example, and just because something doesn't exist on the web today doesn't mean it won't exist in 5 seconds, right? That sort of thing. So the closed world assumption isn't always something that's valid. There are other sorts of negation that you might want to deal with and so forth. So it gets very tricky. In practice, the way I try to deal with things is, and also these negations, these forms of negation can inhibit your ability to run backwards, to treat the inputs and the outputs as equivalent. So another approach, the approach that I try to use generally, is to use constraints, sort of like the finite domain constraints for numbers, to use certain constraints that restrict things or have sort of like an implicit, very minimal source of negation. So just like there's an equal that performs unification, there's a disequality that says that two terms can never be the same. Okay, so that's a very limited form of negation. It's not full negation, it's a very limited form of negation, but because it's so limited, it actually turns out to be useful, and you can write programs that run backwards. Similarly with the numbers, so you can say x is less than y, you could also have something saying x is not less than y. Okay, that's a very limited form of negation. You can only deal with less than and numbers when you do that, but because it's so limited, then you can actually construct examples and witnesses and things like that. So So I think it's the constructive nature. If you're doing constraints, you can often come up with constraints that allow you to express minimal forms of negation. But then once again, you have this problem of if you have this more general form of negation you're trying to express, it may be difficult to rewrite that in terms of these smaller forms of constraints. And that's a constant problem. That's a constant problem. Yeah, so that's a very good question. Negation is tricky. I spend a lot of time trying to figure out how to get around issues with negation.
Does prolog have negation?
There are forms of negation just similar like what I said, where you'd have things like the closed world assumption, and then you could make committed choice or use cuts in certain places. But you have the same problem that, first of all, the closed world assumption may not be valid always, and then secondly, you can inhibit the ability to run backwards, to be able to treat things as relations. So there's lots of ways to handle negation, and sometimes you can get away with these things. But so to me, there's a big distinction between a style of programming where you really only want an answer. You're trying to solve some problem, some real world problem. You just want an answer. And in that case, you maybe feel free to add all sorts of impure operators and so forth to speed things up, to express negation. As long as you get the answer and it's correct, you're fine. If you want to do sort of like this beautiful, very relational style, then you have to restrict yourself more. So we'll see like a couple forms of negation in a minute, and I'm going to use constraints to express those. But yeah, if you want to do something really general, like if you want to say, I want a miniKanren program where if another program fails to produce answers, then the miniKanren fail program will do some other thing, right? That's tricky to express.
Hey, quick question. One of the things that's really interesting about it to me is that it's this embedded language embedded itself. You had a whole bunch of different languages that is it ported into those languages?
Yeah.
So does it have more idiomatic syntax to Haskell or to?
So that's a good question. So for the implementations in miniKanren and these other languages, I think your mileage varies in terms of the syntax. So what we've tried to do, in fact, if you look at the miniKanren language, that's the new version, that's sort of the core language, that was designed to avoid the macros as much as possible. So miniKanren's small enough, it only has those 3 operators and then the interface operator. It's actually not hard to port it to pretty much any language. But syntactically, if you can't express binding forms, introduce logic variables or things like that, then it could be kind of crufty to do. But in some languages, like, if you have a language like Ruby, you could probably fake it using blocks and stuff like that, right? Like there are lots of, if you have Lambda in your language, there are ways you can make it so it's not so obnoxious.
Language is pretty.
Yeah, any sort of functional language, I think it's not too bad. Certainly any language with macros is really easy. I haven't looked at the Haskell syntax recently, so I'm not sure what that looks like. But there are people using it in a variety of languages. I do think
it's not some compiled runtime, so it's a library that's been imported to that.
Yeah, it's basically an embedded library or embedded DSL. Yeah. So one way to learn miniKanren is to port it to a language of your choice, right? So yeah. So if you look at, I can just show you real quick. Now this version of miniKanren is actually pretty big. It's not the version in the book, so it's much longer than that version. Even this version, which has a bunch of constraint solvers and stuff like that built in, it's like 884 lines of code. But the original core miniKanren version and the reason schemer is basically, the book is pretty small. It's not 8.5 by 11. It's much shorter. But the implementation is 2 pages side by side. So it's actually something you can port fairly readily.
Do you recommend the book still, or you said it's kind of dated? Is it?
Yeah, so I think the book explains things like the arithmetic system, so it's useful for that. I think my dissertation has a lot of that information in it. It's sort of written at a different level, but I try to make it accessible. And there are videos online, and there's some tutorials you can find online for people explaining like how to do core logic and stuff like that. Well, Dan and I want to update the book because there really isn't like kind of the general introduction that's really up to date. If you really wanted to overdo it, you'd read the book and then you'd look at my dissertation or some of the papers or things like that. But the book has a slightly older language that's not as elegant. So I think between my dissertation and some of the papers that we've had, like I would suggest looking at the microKanren paper probably if you wanted to see the implementation of it, and if you just want to know how to use it, the paper on the Quine generating interpreter might be a good place to start. That's called foreshadowing.
Are there any other languages or communities that are really active in those like the logic, relational kind of programming?
So for miniKanren, it's actually the core.logic Clojure folks are probably the most active in terms of using it. Otherwise, the Prolog community is the biggest one. So yeah, there's a ton of work on Prolog. There's a ton of Prolog books that are out there. The Art of Prolog is a great book. Ivan Bratko's book on AI programming.
I don't know if it was 10, 15 years ago, but there was Oz was.
Yeah, so Mozart, Oz, there's Mercury, there's Curry. Mercury is a very interesting language because that's a systems programming language, for example. It has like a Haskell-like syntax. Mozart, Oz is a multi-paradigm language that supports logic programming. Yeah, so I think, and also Datalog. I don't know if you've seen any of the Datalog systems and Clojure. There's this diatomic system that's sort of like the killer app for Clojure. So Datalog is sort of like a restricted version of Prolog or a restricted version of miniKanren to try to get the citability back. So you can't do like the arbitrary recursion and things like that, but otherwise it's kind of like a limited version of this. So that's been making lots of inroads in the database community. So it's something more powerful than SQL, but less powerful than Prolog or miniKanren.
Now that the functional languages are kind of coming back in vogue somewhat, do you see a resurgence in interest in Prolog and logic too?
Yeah, I am seeing an interest especially from the functional community in logic programming and things like Datalog is definitely pretty hot right now, and things like miniKanren is actually becoming more popular. core.logic is, there are actually people using it in banks and things like that. Every time I go to a conference, like someone tells me, "Oh yeah, I wrote some miniKanren code that's like doing financial contracts or something," and I'm like, "Okay, that's surprising, but that's cool."
In Excel.
Yeah, exactly. So I think there is, I think as people get more comfortable with things like logic program or with things like functional programming, as those idioms like catch on and those languages catch on, I think things like logic programming will become more in vogue. So I see logic programming is starting to become, there's more interest in logic programming now, but it's not anywhere close to the interest in functional programming. Maybe in 10 years they'll change. It might be the next, there are a bunch of things that could be the next wave. Things like dependent types might be the next wave, or, theorem provers might be the next wave, but logic programming could be part of the next wave. That'd be really cool. Because logic programming was actually very popular in the 80s. And then the AI winter and a bunch of other things happened, yeah.
There's some big Japanese initiative. Yeah.
There was the Japanese 5th generation project in the 80s, and that scared the US. And actually the Advanced Strategic Computing Initiative and all the ASCII stuff and HPC stuff, that kind of was a reaction to the Japanese. Japanese were trying to build supercomputers and like really beefy parallel machines to run Prolog and stuff like that. Okay, so that's all cool stuff. You saw the hello world of logic programming. Now I'm going to go from that to something a little more advanced. So we're going to write an interpreter for scheme, or a subset of scheme, and we're going to make that run backwards and see what it does. Okay? Does that sound cool? Okay.
That's the way my interpreters all run.
Yeah. It's going to be like the moonwalking interpreter. All right. So let's put this. Let's call it, I don't know. Let's call it interp. No, there it goes. Never mind. How about eval low? There we go. Cool. So I'm gonna load our miniKanren up. All right. So before we get into that, let me show you one or two other things in the language that are more extended. So I briefly show you the constraint logic programming stuff. I didn't really show it in action, but we're not going to worry about that right now. What we are going to use are a couple of these constraints that give you sort of either limited forms of negation or something similar to types. Okay, so one thing we're going to have is symbolo. So symbol is sort of like the scheme symbol question mark predicate. So if I do symbol question mark in scheme, is 5 a symbol? No. Is quote foo a symbol? Yes. Okay, so it's a similar sort of thing here. So if I say symbolo of quote foo, that will succeed. Symbolo of 5, that will fail. And if I say symbolo of q, what do I get back there? Well, I don't know. Can you all read that? Do we need to turn any lights on? Okay, so basically we get an answer back saying q is bound to some, it's actually not bound to any specific value. The _0 represents an unknown value. So this q could be anything, but it has this side condition or constraint on it saying that q has to be a symbol. That's what the sim says. So I can demonstrate that by saying if we unify q with 5, now it's going to fail because of the symbol constraint on it, the symbolic constraint. In fact, I can reorder those and it's still the same thing. But if I unify q with quote foo, now we say the query variable is bound to foo, and the symbol constraint we got rid of it because now we actually know what q's value is, so we don't have to have a side condition saying it's a symbol because it is a symbol. Okay, so symbolo lets us say that whatever value q is associated with, or whatever term or value, a variable we put in the symbolic constraint, that thing has to either be a symbol or it has to become bound to a symbol. Okay, that's the constraint on it. Similarly, we could have a number-o. I don't think we'll be using number-o right now, but number-o works exactly the same thing, or the same way. So if we don't have any, if we just have the number-o constraint, we see a side condition saying that the unknown value for q has to be a number, and we can try unifying q with 5, let's say, and now that succeeds. So q is 5. Got rid of the number constraint because it's not needed anymore. So symbolo and number-o let us express sort of the types of those things. Yeah.
Do you need projection to implement those?
Nope. These are fully relational. So there's so notice that so projection is a way to take a variable, the value associated with a variable, and actually get your hands on it, because Scheme doesn't know about logic variables, miniKanren logic variables. miniKanren logic variables are actually implemented as vectors internally. So if you try doing, something like if I associate q with 5, right? Then I might try doing something like, let's just see what happens if I add q to q, right? Well, I get this weird error saying hash q is not a number because that's actually a representation of a vector. So I can't add two vectors together. So I'm leaking how things are represented, how logic variables are represented. What I can do is use this thing called project. So project will let me project q and say that within the body of the project, instead of being a logic variable, now I'm going to be a lexical scheme variable where q is now bound to 5. So if I add 5 to 5, that will work. But actually in this case I'll get an error because this project expression will evaluate to 10, and then miniKanren doesn't know what to do with 10 because it expects a miniKanren expression there basically. But the point is this project operator lets me take a variable, a logic variable, and then get the value associated with the logic variable. That's inherently unrelational, so I don't use project. Okay, that's a Prolog-y type thing. So Prolog programmers would use things like project. Okay, so if you're doing Prolog style logic programming, project's a very useful operator. If you're doing relational things, you want to make things run backwards, generally project's not that helpful. The only time it's helpful is if you want to debug things. Sometimes you can use it to print a value when debugging, but otherwise I try to avoid that.
So it seems that, so are you saying then like project could almost work like a unquote if this was a,
So the problem is that Scheme, like when you say q is 5, right?
Right.
What that means is, okay, let me show you something. I'll do begin, right? So I'll do this, here's like a little hacking here. I'm gonna hack miniKanren a little bit, or the implementation. So what I can do is I can have a begin expression, so I can sequence things, whoops. And what I can do is I can say print, let's print the value of q, okay? Let's see what Q looks like. Okay, and then I'm going to have something that just succeeds. Let's say hash f and hash f. Okay, so if I run that, oh, whoops. Yeah. Okay, so we can see what got printed is that Q is actually this vector that contains the symbol Q. If I actually want to see what value is associated with it, now I have to do a project. So what I could do is I could project Q, okay, and then do the same thing. And now what I see is that Q is 5. So in order to get the value associated with Q, I have to use this project thing. Otherwise, it's some vector that somewhere in miniKanren land is associated or mapped onto 5. There's basically an environment type thing that we build up. So there's an association between the logic Q and the value 5. In order to get your hands on that value 5, that scheme knows nothing about, you have to use the project operator.
So can you use project like as a foreign function interface?
It's a little bit like a foreign function interface when you want to interact with the rest of scheme. It lets you kind of break the distinction between scheme and miniKanren and do some schemely things inside of miniKanren. It's sort of though like breaking abstraction of a monad or something like that, right? Like, yeah, maybe you can do it, but you're like you really are on thin ice when you do that, okay? So that might be a good analogy. Okay, so we have symbolo and numbero, which are constraints that sort of say that, you know, this variable or term has to have this type, basically. The other constraint I want to show you, two other constraints I want to show you. One is called a disequality constraint. Okay, so we already know that if we want to do something like unify Q with 5, we can do that with equal. Q is now 5, but we can also do this. We can have a not equal or disequality constraint. Now we're saying Q can be anything but 5. Okay, Q can't be 5, it can be anything else. And in fact, just like with those other constraints, now we see that the query variable Q, sure enough, could be anything with the side condition that value representing Q, the underscore dot 0, can't be 5. It can be anything else, but it can't be 5. All right, so how can I actually show this working? I can try unifying Q with 5. Okay, and that will fail because it can't be 5 and not 5 at the same time. Order doesn't matter, so that's fine. Okay, now if I make Q something else like 6, that's fine because 6 isn't 5, and I throw away the disequality constraint because it can't be violated. Okay, so we have disequality constraints to say one term is not the same as some other term. And we have symbolo constraints, numbero constraints. And the last thing I have is this kind of weird thing called an absento constraint, saying that some term is absent from some other term. Some term doesn't appear within another term is what it really is. This is a constraint I stole from nominal logic programming, which is a way of dealing with scope and binding of variables and things like that. I'm not going to get into that because that's a whole other topic. But so this absento thing turns out to sometimes be useful, and I think we might see it. So absento, what we can say is that 5 doesn't appear in some term Q, for example, and we'll see once again our constraint on it. Okay, so does 5 appear in 5? Yeah, 5 appears within 5, so therefore we violated the absento constraint because we're saying that 5 can never appear within 5. Okay, does 5 appear within the list 5? Yeah, so we violated there too. Okay, so if we have some deep, you know, we could have some sort of really complicated term, right? And somewhere inside of it there's a 5, that's no good. Okay, and we could have arbitrarily complicated terms in the first position. We could have variables in the first position. You know, we could actually set up Qs here. We could have a absento Q and a Q here, as long as I do the back quoting, all that sort of thing. And that would also be, whoops, absento. Yeah, so I could say like Q here, and can't be in list Q. Okay, and that would be violated as well. All right. Okay, so those are our constraints. In addition to unification, we have disequality, saying two terms aren't the same. Symbolo, numbero, are sort of our shape, or sort of our type constraints. And then absento, saying some term can't appear anywhere within another term. Okay, So that plus unification, plus condy, plus fresh, that's all we're going to need for doing some very cool hacking. Okay? Any questions about that? All right. The absento constraint in particular might look like it came out of nowhere. There's a particular use that might need for it. Let's see. Okay, so let's write an interpreter. Anyone here? How many people here have written an interpreter?
How many times?
Okay. How many people here have written a Lisp or scheme interpreter? Okay, good. Good. So it should be a piece of cake. If you haven't, now you're going to learn. Okay. So the nice thing about interpreter, this is like an evaluator like we have with scheme, right? So it's sort of like this REPL, the reeval print loop, where we can type in things like +3, 4, that evaluates to 7. If we do like lambda x +3, 4, what does that evaluate to? Procedure. Okay. All right, and then we can actually like apply the procedure, pass that 6 or something, and then it'll evaluate the body of the procedure. So what we're going to write is an interpreter for the lambda calculus, the call by value lambda calculus. So it's the 3 parts of sort of like the heart of scheme, the 3 forms that you really need to have in order for your language to be Turing complete. Turns out it's sufficient to be Turing complete. You can write any computable functions just using this. So we'll have variables like x. We'll have applications, and then we'll have lambdas or abstractions. So like lambda x, stuff like that. And we'll have applications, which would be like, x applied to y, okay? Or lambda applied to some other lambda. So those are the 3 forms we're going to implement. We're going to add a couple other things to extend it and after that, but that's it. And once we have that, that actually is like, it really is the core of scheme. We'll just add some other things. In fact, the original paper on scheme said it was an extended call by value lambda calculus. And so this is the heart of it. What? 2 more forms in the beginning, and then I'll show you a couple other things. All right. So, well, gotta remember. So we got variables here. Okay, and we have applications. It's like a E1 and E2, where these are expressions. Okay, so we got application, and we have lambda or abstraction. Lambda XX, stuff like that. Okay, abstraction and lambda. Alrighty. Okay, so what should we call our evaluator? Evalo, sure. Define evalo. Evalo. Okay. And what are the arguments that evalo is going to take?
Expression.
So it's going to take an expression, sure.
Environment.
An environment. Oh, we'll talk about what that is in a minute. What else?
Expression.
Yeah, well, let's be classy and call it val. That's the value you would get from evaluating that expression and in that environment. Okay, so
Get an output environment as well.
Generally not.
Okay.
If you might get like if you're doing if you have state, if you have side effects, you might have an output state, but probably not an environment. Okay, so what is an environment? An environment is a mapping between variables and their values. Okay, because we have variables in this language. So, if we also had numbers in a language, right? Like x might be bound to 5 or mapped to 5 somehow. So when we looked up the value of x, we need to find that there's a 5 there. Okay, so there are lots of ways to do it. There are maps we can use, all sorts of things like that, dictionaries. We're going to use an old school scheme or Lisp approach called an association list, which you may have seen. So it's a list of pairs where the pairs basically are an association between symbols representing our variables and the values of the variables. So, if x is 5 and y is 7, we might represent it like that association list. Okay, so it's a very simple representation. The reason we want a simple representation is that our big hammer is this unification, this equal operator that knows about things like lists and pairs and symbols and so forth, but it might not know about things like maps and dictionaries and so forth. So we're going to do very simple representation of environments. And there are some disadvantages to this representation, but I'm not going to get into those right away. Yeah.
Which version of Racket are you running?
I'm using a version of Racket called Scheme.
No, which, like, version 601 is...
Oh, okay. So this isn't Racket I'm running right here. This Racket is like whatever the latest Racket is. I'm using Shea Scheme. So actually, yeah, I really am using Scheme right here, but you can do most of the stuff in Racket. I will
I'm
say,
trying to follow along with Racket.
yeah.
Scheme interpreter, and it's failing to load.
Yes, so, yeah, I apologize for that. The thing is, the Racket version of miniKanren is sort of under redevelopment. So Claire hasn't released the latest. You should be able to do the things, some of the simpler things here, and probably do this relational interpreter. The load mk.sm.
Yeah.
Could he
Yeah, so actually for Racket, you don't want to load mk.scm. You want to do something like this, require probably.
Yeah.
Which yeah.
Scheme interpreter would you recommend?
Just to get up and running, I would probably use like Petite Shea Scheme, and yeah, and then you can use the mk.scm file that's on my GitHub or whatever for the.
In Racket, you can just type in the command racco pkg install cKanren, and it should give you the latest cKanren installed on the GitHub, or on Claire's GitHub.
Yeah, unfortunately, partly because we have so many different implementations and ports of this, it's like it's not one-stop shopping. And you know, I could also say, hey, you could do this all in Clojure and core.logic, but that also has kind of its own set. You know, so we sort of have the Lisp tradition of having many incompatible dialects. You know, it's like it's a glorious tradition in Lisp and Scheme. And
you use the R6RS compatibility in Racket?
I don't really think that's the problem. Actually, I think there's probably something else going on or something else missing. So yeah, I'm happy to look at it offline, but I think I intentionally tried to avoid that issue of getting everyone synced. But I will try to help you afterwards, hopefully. And the other thing is I can put this code online. So no, I'm definitely happy to help people get it running. Okay, so we want to have an environment that's going to map variables to values. All right. So that's what the env part is. Okay. All right. And in fact, you know, well, no, I don't want to get into that one. Okay. So when we're writing a val, what should I write next?
Symbol.
Symbolo. Okay. Symbolo of what?
Expert.
Expert. Okay, so that's one of the cases, right? So, because we have 3 different cases for lambda calculus, so since I have 3 different cases, what else am I going to need before I get to this? Condi, right? Okay, so I have three cases for lambda calculus. So the 3 condi clauses, and the first one will be the variable clause. So we have the symbolo. So now we know we have an honest to goodness symbol representing a variable in the first case. Okay, so if I give you a variable like x, I want to know what's the value of x, and you tell me.
It's the value in the environment.
It's the value in the environment, right? You have to look it up. You have to look up x in the environment to figure that out. Okay, so we're going to need some way to do that. And so let's write a little helper called lookup. And in fact, what I'll do is I'll comment out these other clauses for now. So we'll have an honest goodness evaluator that only knows about variables, but we can actually test it. Okay, so we're going to have a lookup. We're going to look up the symbol, the expert, in the environment, and the value of that will be the value of the entire expression. Okay, so now we just have to write lookup. And lookup is just going to take one of these association lists and look it up. So that shouldn't be too hard, just standard recursion. So let's do lookup. And what are the arguments that lookup is going to take? How many arguments are going to take? 3, right? We can see from the call. So we've got, you know, like a variable like x. We've got some environment in, and then whatever the val is that's associated with, right? Okay. So how do I know if I've, you know, how do I write this lookup thing? Condi, that's always a good choice, right? All right, so we got some cases here. I don't know how many there are going to be. Start out with 2.
Or how do you blow up on this empty list?
Oh, okay. Well, let's try to figure this out. So if the environment is empty, so what is the binding then? What's the value of x?
If there is one.
So if we were writing this in regular scheme, we would probably have a call to error saying lookup O, x is unbound or something like that, right? Well, what happens if we try something in miniKanren and it doesn't work? If something we're looking for doesn't exist or whatever,
Stop your search.
the search stops and we say we fail. So instead of dealing with things like errors, we just say that we're not even going to add that case and it'll just automatically fail. So that's a very nice thing. So something that would give us an error, an unbound variable lookup, now will just not give us a solution. So that's kind of a nice.
So you don't even look for the case.
That case is gone. So we will not have that case, and we actually won't have a base case in a sense. Okay, so it's kind of weird, but kind of neat. Okay, so what would an environment look like if it's not the empty environment?
Would it be a list of key value arrows?
Yeah, so an environment might look like something like, here's a key and here's a value called v1, key 1, v1, right? And then here is the rest of the association list. And that might be the empty list or it might be something else, okay? So that's what it's going to look like. And in fact, I'm going to pull that out. So let's introduce some variables here. Okay, so we know k1 is a variable, v1 is a variable, rest is a variable. And we can just go ahead and do this unification here outside of the const. Okay, so we're saying that the environment, because we know it's not the empty environment, the environment has to have at least one binding between a key and a value. And it's not just a key, it has to be some variable, right? Some symbol representing a variable, so like y and some value. I don't know, I'll even call it val. Okay? Okay, so that's what it looks like. I guess if I really wanted to do it right, I'd probably do this way. Okay, so is y what we're looking for? Could be, could not be. So how do we know if it is? How do we know if it isn't?
Unify.
I'm going to unify. Okay, so let's say x and y are the same, right? If x and y are the same, then what's the value we want to return from lookup O?
V and val.
So v and val then are the same thing, right? Okay. What is my other case then? I'm going to call lookup O. Oops. Lookup O of what?
That's
On the rest is the end, but what's the variable I'm looking up? Is x and the rest,
and val.
and that's val. Okay? We all happy with that? Okay, so let's try this. Great. Okay, so we've got lookup O here. Actually, let me make sure I've loaded whole thing. All right, so let's try our lookup O. So actually, you all should now be able to tell me what's a test case I can write for lookup O. Run one. Q.
X.
X, quote X, sure.
Quoted list containing a single pair mapping x to say 5.
Okay. Okay, and then the output value. So what should we get back?
5.
Is it 5?
Listen.
List containing 5, right? Sure enough, that works. What happens if I do a run 2?
Hopefully we'll just still be 5.
So the program works, right? Okay, let me ask you this.
5 and 7? Yes.
Is that a good answer?
No.
If not, if we believe in shadowing of variables in lexical scope, right? Because this could appear like think of it this way: if we had something like let x be 7, and then inside of the let we had let x be 5, with our representation of the environment, and we're looking up x inside, we want to get 5, not 5 and 7 as different answers, right? So we want to be able to shadow. So let's look at our code. So what's wrong with this definition?
The lookup doesn't have a disunification between.
Yeah. So here's the weird thing about miniKanren. When you ask for all the answers, not only will it try this answer, it's like, hey, x and y are the same, but even if x and y are the same, it will also try this answer. It will try this clause. It will try them all the time, unless you explicitly tell it otherwise. So we have to explicitly tell it otherwise and say x and y can't be the same. If they're different, then do the recursion. Okay? So we actually have to guard that. This is the equivalent to having the else, right? If you had an else here, where one you're saying are x and y equal, now we're saying they better be not equal. Okay, so we have to guard it. If we do that, then we should be okay. So let's see. So
The not equal only works
Yeah.
for primitive types, is that right?
it works for any two terms. And so you could have lists that have variables in them and things like that. Basically, it's just going to say that. Well, okay, so that's a good question. So let me show you. I didn't show you the full range of this quality constraint. Let me just show you one or two real quick. A little more interesting. So I could say, for example, like here are the primitive types. 5 and 6 are different, right? That's different. I could say Q and 6 are different. That's fine. But I could also do things like with pairs. So I could say fresh XY. And I could say, for example, that x dot y is different from 5.6. Okay? And now I can say that Q is the list XY. And now what I'll see is Q, the query variable, is bound to a list of these two variables, x and y, whose values we don't know. But we know that x can't be 5 at the same time that y is 6. I can make x 5. That's actually fine. If I make x 5, that's okay. But if I make x 5, then y, which is still unknown, had better not be 6. I can't make x 5 and y 6 at the same time. So if I add this extra unification of y and 6, then it'll violate the constraint. Okay, so you can have very complicated terms of variables all over the place, and it'll solve them in the right way. Okay, yeah.
Let's say you use the same constraints, but instead of taking a list of x and y, and you just brought out y, would it still show you?
Oh, okay. I see. So you want to know how it's going to be reified? If it's how the constraint will appear?
Yeah.
Yeah, that's a very good question. So let's get rid of. So do you want to still keep those two, or?
Yeah, you can.
So you just want to see the value of y printed now?
Sure.
Okay, in this case, since it's violated, it doesn't make any difference. But let's get rid of these x and y unifications. Now you'll see something very interesting. You'll see that we don't see any constraints anymore. And that's because there's no way to violate the constraints given the information returned. It's like you'd have to have your hands on x and y in order to come up with assignments of those that violate the constraint. So miniKanren's unifier is smart, and it's only going to give you information you absolutely need to make sense of the full
Alright,
answer.
so what if we constrain one of them? We can constrain x to be 5, and then y can't be 6. Is it going to
So so do you want two different disqualify constraints?
Unify x with 5.
Okay, unify x with 5. So now this is forcing y to not be 6, right?
X with
Oh, whoops. Sorry. Yeah, then it's throwing the constraint away. Yeah, and now you'll see that the constraint on y, which is the only relevant one, is still printed out. So the reification rules, they all make sense, but
But it looks like the side constraint is.
because y and q are the same, it's basically saying that q can't be 6 now, right? So yeah, so actually writing the reifier the reifier is the part that prints out the constraint in sort of a minimal form. That's actually harder usually than writing the constraint solver. It's writing the representation of the constraints is really tricky. Those are all good questions. Okay, so now with lookup we can add this disequality constraint, and therefore we're guarding the recursion basically. And furthermore, that means we can safely swap the order of the condes without changing anything about the semantics, right? So that's really important that we be able to reorder things without changing the semantics, as long as there actually is an answer that exists. So
Did you reorder for this reason?
now I just reordered it to be perverse. Yeah. So it doesn't actually matter. Like, I mean, miniKanrens with the condy clauses, it doesn't really make a big difference in this case. If you really wanted to do something the most efficient, you'd probably do it this way to make the recursions come last. But with the disjuncts, with the ors, condy top level clauses doesn't really matter. It's only when you have the conjunctions that it matters. Okay, then it really does make a difference. Yeah.
So earlier you were talking about conde and
Conde and condu. Those are committed choice operators, basically.
Okay. Do the order matter in those? Or
Yes, they absolutely matter, because what conde is saying, or condu is saying, is it treats this first goal, let's call it a goal, these miniKanren sub-expressions, treats the first goal in the conde clause as special. It treats it as an actual test. And if that test fails, then it moves on to the next clause. Otherwise, it commits to that clause and will only give you answers from that clause.
Oh, so if you did conde, you wouldn't need that disequality.
That's right. So conde acts much more like regular cond or if, but that's the disadvantage of it as well, because if you really want to do full relational logic programming, you want the full power of condy. You don't want something that acts more like if. You don't want to commit to one branch but not the other, because then you're losing answers when running backwards, that kind of thing. So you do have the power to do something that is more like an if or a cond, but you should use that very judiciously.
Disjoint, right?
Here the branches are disjoint. They're non-overlapping, we say.
Conde?
It gets... The conde, when you can use conde, it starts getting very tricky. When conde is really tricky is when you have a fresh variable in the test position that becomes ground. If the variable becomes ground through unification, which means it has no more variables in it. So if you have something like a unification in this test position of a conde, and the variable then becomes instantiated, it gets a value, that's bad. That's really bad. And in general, that's unsound. So you can actually do things that logically don't make sense. So you can get a lot of trouble with conde and condu if you're not really careful how you use it. It's equivalent to cut in Prolog to some extent. So I'm not going to talk about those in too much detail other than to say they exist. They talk. I talk about them in my dissertation. Some I talk about in the miniKanren book, but it's more like the Prolog type stuff. Okay. So I'm going to show you something. We're going to say pure. Okay, we're not going to use conde or condu. We're going to do everything the right way, which means that we actually have to have these disjoint clauses. Okay, we actually have to make sure that we're not going to have overlapping clauses, and the disequality constraints make that happen. Okay, so now we have lookup. So our evaluator is the third finished. We actually have now an evaluator that can deal with variables and environments. So now we can call evaluo, and since evaluo is calling lookup, so that works. So we can evaluate a variable that happens to be bound in the environment. What's going to happen if x isn't bound in the environment? Yeah, it's like it's going to fail, has no answer. Okay, so.
And can you do it in reverse?
Can we do it in reverse? Now you're starting to, okay, good. Okay, so let's say the value is 5. What's the value of q that would make this 5? Q is the variable. What is that? Y. That's it. It's y is the only value. Okay? Or we could say y is 5 and the environment is q. What are we going to get back?
Y5.
Where y is 5?
Oh, wait. Hold on. Quote y. Sorry. That's a symbol. Okay. I'm going to get back.
Well, there's infinite cases. So it's a 1.
So
Okay, let's just start with a 1. Okay, so we get an environment where y is bound to 5, and who cares what's in the rest of the environment? Doesn't matter. Okay, let's get a second answer. Any predictions about the second answer?
there'll be something before the y equals.
There'll be something before the y is 5. So here we're saying some variable is bound to some value. We don't care what they are. And then we have y bound to 5. And then we have the rest of the stuff which we don't care what it is. But that first variable at _0 cannot be y. It can be anything else, but it can't be y. Okay? Because otherwise we'd shadow it. That's like a very general answer, isn't it? That represents infinitely many environments, right? That's a cool answer. I like it. That's a nice answer. So, okay, that's good. So, glad we ran it backwards, okay? Cool. What's that?
Is 3 just going to be one?
3 is going to be like more of the same, right? So we have 2 things in front of the association, and we have 2 disquality constraints now. Yeah. Okay. All right. So that's good. So even just variable lookup starts to get interesting, right? And there are all sorts of ways we could represent environments other than the way I showed you that give you some interesting trade-offs. All right. So that's one. So what else? So we still have 2 other things. So we did variables. That's done. Okay. What else? We have Lambda and we have application. Which one do you want to do? You want to do Lambda? Okay. Fine. So how do we know we have a Lambda expression?
Symbol of the list. It's a list with the lambda in the first spot.
Yeah, so it looks like lambda, some variable, x, and then some body, right? Okay, so that's what it looks like. And we can unify that list with the expression, that's right. So it's sort of like pattern matching, right? We're using unification sort of like pattern matching here. Now, of course, we've introduced some variables, so we better introduce those in our fresh. Okay, so now we know we have an honest-to-goodness lambda expression. What's the value of a lambda expression? Well, it's a procedure, and we can represent a procedure as something called a clojure, which you may have heard of. So a clojure is basically a combination of sort of the code of the lambda expression plus the environment. Okay, so we can represent a clojure. One way is like as a list, so we can give it a clojure tag. So it's just going to be a tag list. We're using the symbol clojure. And we have the information from the lambda expression, like x and body. And we also have to have the environment, because that's how we know, that's how we get our nice lexical scope with our clojures. Otherwise, we've reinvented old Lisps and Emacs Lisp and have horrible dynamic scoping, and we're not going to go down that path. Okay, so what we're going to return is an honest-to-goodness clojure that saves the environment in it and has the variable in the body. Okay? All right, and that's going to be your value. Okay, so that's a clojure representing a procedure. So that's the value of a lambda expression, and we can actually try that now. So we can try evaluating a lambda expression, say in the empty environment. Okay, so we say lambda yy. And we should get back a clojure if we've done it right. Sure enough, and there's only one answer, so run 3 is fine. So we get clojure containing the formal parameter y, the body y, and the empty environment, which is the environment we evaluated that lambda expression in. Okay, so we're down 2 of the 3. Okay, now we've got one more thing, which is an application. What does an application look like, a procedure application? Just parens with 2 expressions, right? That's the beauty and horror of Scheme, is that, you know, an application looks like E1, E2, right? If you love the parens like I do, then that's a beautiful thing. So the expression is going to look like that. Okay, it's just a list with these 2 sub-expressions, and we're going to need to introduce some fresh variables. Okay, now's the interesting part. How do we actually evaluate an application on Scheme?
And usually it's a helper function.
No, we don't do helper functions here.
Basically, just extend the environment.
We're going to extend the environment and then call what? Okay, so we're going to do some sort of extension of the environment. So we have env here. We're going to extend that somehow. Okay. Okay. And env is going to be extended between what and what?
You're going to do a recursive call to evaluate.
Oh yeah. So we have to evaluate what? What's our expression we're going to evaluate? First we're going to evaluate E1, right? Because we don't have a body yet. Okay, so we have 2 expressions, right? Now at some point, hopefully we will get a body. So E1 in particular, we're going to evaluate that in which environment? The current one, env, yeah. And what should that give us back?
The closure.
So if we're evaluating some procedure that we're going to call, that thing had better be represented as a clojure. And we know what a clojure looks like. A clojure looks like this thing up here, right? So when we evaluate that E1 in the end, we better get back something that looks a lot like clojure x body env. Okay? So we can just use that actually. Okay. Or env hat actually. So this is going to be the env hat will be the environment in which the clojure was created. Okay, so evaluating E1 gives us a closure, or better. And notice that because of the way this works, unification will fail if it doesn't give us a closure. So if E1 evaluates to 5, it'll just fail. It won't give us an error saying that 5 is not a procedure. It just won't give us an answer back. Okay, so we don't have to worry about getting errors in our system, which is kind of interesting. Okay, so E1 evaluates to that. What does E2 evaluate to? Better recur on that too. E2 in the end evaluates to something. Let's call it the arg. Arg. Okay, we get an arg. Okay. Now, what do we do?
Reduce it to the body binding.
We're going to evaluate the body, look around the body, in some environment we're going to build, and the value of that will be the value of our whole thing, right? And that value of the environment is going to be our current, well, which environment is it?
You got extended.
The current
It's the environment in the closure. It's the environment stored in the closure. Otherwise, we get dynamic scope. So we have to use the environment in the closure, which is in pat. And we're extending that with what?
with ours.
With the binding between arg and... So x is our formal parameter. If you haven't written interpreters before, this actually is, it's a little subtle. So x is bound to arg. Okay, that's the new extension to the environment we're making. The old environment is going to be in pat. Okay? I think I got it right. So the idea is that we have two expressions that are involved in this application. We evaluate each expression independently. The first expression had metaphorically better represent a procedure. So we expect it to turn into a closure, to evaluate to a closure. The second thing just has to evaluate to some value. We don't care what it is. But that value we get, the arg, we're going to pass that arg into the closure, binding it to x, which is the formal parameter, and then evaluate the body in the extended environment, the extended saved environment in pat, with that new extension, binding between x and arg, okay? So those are all the parts. That actually is really tricky. I mean, this is basically a quarter of a programming languages course is figuring out how to do that last line. Okay, so don't feel, and in fact, if you do things like just remove that hat, you get totally different behavior and stuff. So, don't be surprised that this is like a little subtle, but if you understand that code, actually, you'll really understand like the heart of Lisp at a very deep level. Okay, so that's our evaluator. And so now we can actually run it. Okay, so let's try doing like a simple reduction here. So let's just say lambda yy applied to, lambda zz. Okay, and that should give us back the lambda zz represented as a closure, and sure enough it does. So we did a simple application. All right, so that actually works. We're applying a procedure to another, a lambda expression to another lambda expression. Seems to work. Okay. So that is a miniKanren interpreter, and we can make it run backwards. So we can say, all right, say we want the output to be the closure ZZ, right? We can say, what is an expression that evaluates to closure ZZ? Anyone give a... Lambda ZZ, right? That's the simple thing. You don't have to do an application, right? So lambda ZZ is one example. Let's try again a second one. Whoops. So a second example would be this application. Lambda anything. This is the identity function, right? Apply to lambda ZZ gives you back that closure, right? Okay, let's get a third one. Okay, and then here, what is this? This is some complicated mess. Let me just pull that out. So that's, nested lambdas and another application. Wow, that looks kind of hairy. I don't know if this is actually true. Well, let's see if it works. So one thing we can actually do is run this in Scheme. Okay, sure enough it gives a procedure, but is it really the identity procedure? So let's try by giving it 5. Sure enough we get 5 back, so that's real, okay? All right, so that's fun. We can push that a lot further. And I'm not going to try your patience with showing the two extensions, but let's just let's pretend we added two more things, okay? And it turns out it's not really much harder than this. We could add quote. So, like quote of foo is the symbol foo, right? So quote of datum in scheme gives you back datum. So quote of +3,4 doesn't give you 7, it gives you back the list 3,4. So we're going to add quote to our language, and we're going to add list. And list we know and love, so like list 345 gives us back the list 345, okay? So let's pretend that we added those to our implementation. They're actually pretty simple to add. Well, these actually are like built into the language we're writing the interpreter for, so we don't even have a listo, although we could write a list oxo as a helper function, okay? So let's pretend that we've written those helpers, and yeah, so when we do that, the quote line looks kind of like this. So here we've got quote of datum, and it's going to evaluate to datum. That's what we're seeing here on the right. Okay, and I've got this side condition not in environment, basically row is the environment. That side condition is to make sure that we handle shadowing properly, so that we can actually shadow things like quote and list built in the interpreter. So we can have Lambda quote and this system will work properly. So anyway, that's like a technical detail to try to get everything right. It doesn't really matter. And then list has this eval listo, right, helper function, okay? So, but otherwise is basically what we just wrote. It's equivalent to what we just wrote. I represented Clojure slightly differently. But, so now we can have some fun. So let's try this. Okay. So now that we have lists in our language, we can run things slightly different. We can have slightly more interesting examples. So we have eval expo here. So let's see, run one q. And here we're calling it eval expo instead of eval. It doesn't matter, same thing. Eval expo, and this time I'm taking the environment first, and then some expression. Let's just show you that actually still works. Still lambda yy, and then here's q. Okay. So here I'm just representing the Clojure a slightly different way. So the thing behind in is the environment. And then instead of having the formal parameter and the body represented separately, I just stuck the whole lambda expression in. It's equivalent. But anyway, that's a Clojure. Okay, so that's fun. And I have lists. Remember I told you I have list, right? And quote. So now I can do things like list of quote of 5, and that evaluates the list of 5, okay? And now I can start playing interesting games when running backwards. So now I could say, give me an expression that evaluates to the list, I love you, let's say. Okay? What's an expression that evaluates to I love you? Well, list, quote, I, quote, love, quote, you, right? That's one of them. Or just quote of the list, the actual verbatim list, I love you. So let's see if we get the one you mentioned. Not yet. It's in there somewhere. Here's a list of quote, I, quote, love. I don't know. We have to keep looking, right? So miniKanren's going to like kind of generate things the way it wants to. But yeah, you can see it's quote. Like let's take this one for example, right? That's kind of in the same spirit. So we have a list of quote I, and then we have an application of a lambda expression, the identity function to the quote love, and then we have quote you. And let's evaluate in scheme, and sure enough, it evaluates the quote I love you. And Matt Might has this blog post on 99 ways to say I love you in Racket. It's like, well, that's boring. I'm not going to write 99 programs by hand. I'll just do a run 99, and then, you know, and then they come back, right? So like here's one. And I can actually just run them and actually show they work, right? So like here's some nasty looking thing. Like what is? Well, yeah. So he's got like nested applications and stuff, right? So sure enough, that works. Okay, so that's fun. Now let's try something a little harder. Okay, so what if? Okay, do you all know what a quine is?
a program that emits its source code. Like,
So a program that evaluates itself or emits its own source code, right? So what if we wanted to generate a quine with our relational interpreter that could run backwards? We have an expression, an environment, and a value. So how would I generate a program that evaluates itself using that? The expression's the value. Okay, so here's the environment. Let's just do 1 instead of 99. So, okay, so how would I represent that? Just Q. Well, that can't work. Get it? Huh. Okay. Let's grab that. Oh, that's pretty good, isn't it? Okay, let's try something harder. That's too easy. Do you know what a twine is? Or twines are? Twines are two programs, P and Q, where P and Q are different, where P evaluates the Q and Q evaluates the P. Can we do those? How do we do those? Set up calls of Val Expo, right?
yeah.
So we need 2 of them. All right. So let's yeah. So let's have a query variable like R or something. Well, I don't know, what should we call it? X, right? And then we'll say fresh, P and Q, right? All right. Cool. So P evaluates the Q. Q evaluates the P. Let's see if we can find things. Oh, unify X. Good point. By the way, I'm not. I really should be using the. I'm using the interpreter, not the compiler, so it's running a lot slower. But P and Q. Whoops, backwards. Okay, so let's try this again. We forgot something in our program, by the way. Wasn't quite right. Oh, maybe it worked. Well, so the thing is, we didn't put in this constraint that P and Q should be distinct, right? In this case, it looked like they are, but what we really want to say in P and Q are different, like that. Okay, so now it's really the definition of twines. And let's see if it works. And sure enough, okay, so this expression up here has a quote in front of it, and then the expression down bottom doesn't have a quote. And if we evaluate that, we better get something back with a quote on it. Yeah, sure enough. And when I first was showing this to someone, some of the audience was like, well, that's not a good twine because the only difference is the quote. And I was like, I'm sorry. I'm sure your quine generating relational interpreter is much better than my quine generating relational interpreter. But yeah, I mean, I think that's just kind of the nature of twines is they kind of have that shape. You can also do thrines where P, Q, and R go in a cycle and all sorts of things. What was that?
Well, they have these quine relays that go on.
Yeah, so like the quine relay
you
stuff.
could do that if you had made an interpreter for all those languages.
Exactly. So that's an exercise for you. No, not for you in particular. Okay, and then one last thing I'll show you. I mean, there are all sorts of games you can play with this stuff. It's really cool. But I'll show you. Yeah, the full eval. Okay, so remember those numbers I showed you in the beginning, the Oleg numbers, right? Well, this is that quines generating interpreter, but extended with the arithmetic system as well. Okay, and some other things like if and stuff like that. Okay, no macros. That's hopefully coming soon. Okay, so let's load this one, and then we've tagged the numbers here. So I can say, let me make sure I get the right interface here. I think these are called. Okay, so I can just do a eval. So run. Okay, so run 1Q of eval, and let's say, I'm going to say, I think it's int exp is the expression, and let's say 3, okay, and that's going to evaluate the Q, and int val, okay, so cool. All right, so here I'm saying I've got tagged integer expressions, and they return tagged integer values, so I can do, for example, like 6, right, so 6 would be that. Okay. Then this one I have a helper because normally I'm running it with the empty environment, so I just have a helper. But if you really want to play with the environment, you can just use the full eval expo that takes the environment. It's just convenience. We could do it either way. I mean, let me do it with that one. Eval expo, I think it's called eval expo, and this one I think takes the environment in second position. empty environment. Okay, same thing, right? Okay. Now what we're going to do? Go run it backwards, right? So we're going to say we don't want 6 to be the input. We want 6 to be the output. Generate a scheme program that evaluates the 6. So what's the scheme program that evaluates the 6? 6. Okay. Something a little more interesting. Lambda nil applied, right? And okay, fine. more better than that. Sub 1 of 7. Okay, that's kind of cool. Okay. All right. So let's see. Here's one. Here's a multiplication of 6 times 1. Here's one multiplying 2 by 3, right? And if we do like 50 or something, let's see if we get anything interesting here. Ideally, what you really want. Okay, so here's one. Like, yeah. So here's one that has like land. Oh, here's one car of cons, right? So what is this? It's saying the car of cons of 6 to quote of any symbol at all. Now here I can't do it directly in Scheme because like that actually should be 6, not in X, but I can do that, and sure enough, that gives you back 6, right? So, and if you're doing the finite domain constraints, you actually can use 6 there instead of the Oleg tagging. So here I'm basically enumerating Scheme expressions that will evaluate to 6, and I can put in other values that I expect, like lists or things like generating clients. And you can also play tricks. I've got another evaluator that will do things like generate the Y combinator or fixed point combinator and things like that from the mathematical specification. And so anyway, this is lots of fun. There are lots of programs. You can also write type inferencers like this where you give the type of the expression, like int arrow bool, and it starts generating programs that have the type in arrow bool or expressions that have in that arrow bool or whatever, right?
You have it write a program which will write Shakespearean novels.
Yes, like the British Museum algorithm with the monkeys. I'm not sure about that, but there is someone who's kind of infamous for posting to the Usenet list complang scheme and posts all these very simplistic posts. I think the person's a troll, but I thought about writing a miniKanren program that would just like write posts in that style and just kind of have like a bot that would, a troll bot. Yeah, the scheme Usenet list doesn't need any more trolling though. So anyway, so hopefully this gives you some sense of the sorts of programs you can run. And it gives you some idea of like what happens when you look at the world backwards, right? When you can start thinking about, there's nothing special about the output, right? The output should be able to say, here's the output I want, give me inputs that I don't know, stuff like that. So, and you can do that even with things like interpreters.
Can you do that to like explore a landscape? Like would it ever give you something you didn't expect?
It definitely gives you all sorts of things you wouldn't expect. That I can guarantee you. Many times I think I'll write one of these programs and I'll think it's got a bug in it. And it's like, no, it just outsmarted me type thing.
Did you find like some interesting attempts at proofs and stuff? Like,
Yeah, well, these are proofs basically.
Right.
These are constructive proofs, and we have an automated. So we have an automated theorem prover written in this. So in that, not only can you give it a theorem, and it'll give you a proof, but you can give it a proof, and it'll tell you what the theorem is. And
Right.
all sorts of stuff. Yeah, all right.
all right.
Or you could give it part of a proof and part of a theorem, and it'll try to fill in the blanks and stuff like that, right? So yeah. So anyway, that's relational programming and miniKanren, and I hope you'll play around with it. And if you have any questions, always happy to talk about this stuff. Thanks.
Great.